This is the second example in a set of 8 videos that introduce you to nodal mesh analysis. Here we are still doing nodal analysis, and this problem is not fundamentally more difficult than the first problem that we worked, which is this one here, except for the fact that it has 3 or 4 nodes instead of 3, and so we have 3 unknowns instead of 2 unknowns. And we still are working just with resistors and current sources, independent current sources. So you might have noticed last time in the first example that we were always doing some voltage or a difference in voltages divided by a resistance. Okay, so it was always a voltage over a resistance. So it might be convenient to replace all of these resistances with conductivities. Okay, so here we would have, what is that, 0.2 and 0.1 and 0.2. Okay, and so I'm going to use conductivity this time instead of resistance. You'll see that at work in a minute. So notice here we have 4 nodes. One of them has already been labeled as the reference node, and so we have 3 unknowns, V1, V2, and V3. We will solve for those by writing a Kcl equation at each of those nodes. So let's start at V1. So here we have V1 minus 0 volts divided by 10 ohms, or I'm going to write it now as V times G, the conductivity. And I'm going to leave the units off, though that's a bit sloppy. Our second current, the one that's going to be going, so that was current going down through the 10 ohm. Now we have current to the right through the 5 ohm. That's going to be conductivity of 0.2 times the voltage across that resistor, which from left to right is going to be V1 minus V2. And then lastly, we have current flowing up through the 20 ohm, or we didn't label that one. That's going to be 0.05 mhos. So we have 0.05 times V1 minus V3, and all of that equals 0. We can now collect terms, so we could say 0.1 plus 0.2 plus 0.05 times V1, okay, minus 0.2 V2 minus 0.05 V3 is equal to 0. And this here is 0.35 mhos. All right, now we proceed to the Kcl at node V2. And here we will have current leaving through the 10 amp source, so that's going to be minus 10 amps, okay, plus the current leaving to the left, that is going to be 0.2 times, and now we're going to go V2 minus V1, right, because current leaving would correspond to the voltage V2 plus over here minus to the left at V1. And then lastly, current leaving to the right through the 10 ohms, so that's going to be plus 0.1 times V2 minus V3 is equal to 0. We can collect terms again. We will have minus 0.2 V1 plus 0.2 plus 0.1 V2 and minus 0.1 V3, all of that equal to 10 amps. Lastly, node 3, we will have 0.2 times V3 minus 0 plus 0.1 times V3 minus V2, that's the current going to the left through the 10 ohms, and then finally the current flowing up being 0.05 times V3 minus V1, and all of that equal to 0. We collect terms, and we'll have minus 0.05 V1. We have minus 0.1 V2, and then we have 0.2 plus 0.1 plus 0.05 times V3. So this is 0.35. Okay, and we can finally, now we can put this in matrix form. Okay, you could solve this by substitution, it's just going to be a little bit more work, or you can use a program calculator to solve this set of equations. So we have V1, V2, V3, and then looking across in this first equation we have these coefficients. So we will write 0.35 minus 0.2 minus 0.05. And then the second equation we have minus 0.2, 0.3, and minus 0.1. So minus 0.2, 0.3, and minus 0.1. And lastly, we have minus 0.05, minus 0.1, and 0.35. So minus 0.05, minus 0.1, and 0.35. And all of that is equal, over on the right, we see that we have 0, 10 amps, and then 0. Okay, 0, 10 amps, and then 0. So this is our final answer here. Well, we haven't solved for the voltages, but this is, if you were asked to just set up the problem, this would be the solution. And again, this is the conductivity matrix, this is the voltage vector, and the source vector. And I'll just point out, in this case, notice that if you look down the diagonal here, look at what you see. All of these are positive. Okay? And if you look across that diagonal, you'll see that these are symmetric. See that? Minus 0.2, minus 0.2, minus 0.05, minus 0.05, and minus 0.1, minus 0.1. Now that won't always work out, but in this kind of problem where there's just resistor and independent current sources, you will have that kind of symmetry, and so you can actually check your work that way. By the way, the answers to all these problems are in the accompanying notes, and so I'm not bothering to take this any further. The main point of these videos is to just get you to the point of having the n equations and n unknowns, and then you can use whatever math technique to solve that set of equations.